This is what the actual global stiffness matrix looks like for this model. It has some interesting characteristics. It is said to be sparse because it contains a lot of zeros, and banded because the non-zero terms are grouped around the diagonal. For linear elastic problems, the matrix will also be symmetric. If we modify the mesh so that the three elements are connected differently, the global stiffness matrix will change. In this case, we have 3 nodes instead of 4, so the matrix will be smaller, and the fact that elements 1 and 3 are connected is reflected in the matrix. An important thing to note here is that the elements are no longer aligned to the same coordinate system, so we have to transform the stiffness matrix for each element so that it aligns with a global coordinate system. We can do this by multiplying each element's stiffness matrix by a rotation matrix. Now that we've assembled the global stiffness matrix, we need to solve this equation to obtain the displacements at each of the nodes. To do this, we need to define the external loads and the boundary conditions. The boundary conditions are known displacements at specific nodes, typically because specific degrees of freedom are fixed. In this model, vertical and horizontal translations are fixed at node 1, and vertical translations are fixed at node 2, so the displacement vector looks like this. And the force vector will look like this. It includes the applied force and the reaction forces at the supports. Now we can solve the equation. We could do this by inverting the global stiffness matrix and solving the displacements from there. But in practice, inverting the matrix isn't very efficient, particularly because it's a sparse matrix. Commercial solvers mostly use methods that involve iteratively approximating the displacement vector, like the conjugate gradient method. Once we've solved the nodal displacements, we can calculate the strains and then stresses throughout the mesh. A typical finite element mesh could easily have 100,000 degrees of freedom, which would be impossible to solve by hand, and so applying the finite element method to anything more complicated than a very basic model requires the use of appropriate software. Now that we have an overall understanding of the finite element method, let's return to the element stiffness matrix to see how it's derived. The matrix shown here is for a 2D beam element, but it will look very different for different element types. Several different methods can be used to derive these stiffness matrices, and they are all fundamentally based on the concept of equilibrium. The direct method derives the stiffness matrix directly from the equilibrium equations that govern the behavior of the element. The lateral deflection of a beam is governed by this equation, for example, so we can solve the equation to obtain the stiffness matrix for a beam element. These governing equations are usually differential equations. The differential equations and associated boundary conditions are what we call the strong form of the equilibrium problem. But it's only really possible to solve the strong form for simple elements. For more general cases, we can use weak forms that describe the differential equations in integral form, instead of solving the differential equations directly. These give approximate solutions to the equilibrium equations, but are easier to solve. The first of the weak form methods is based on variational principles. One such principle commonly used for structural mechanics problems is the principle of minimum potential energy. It states that the displacement configuration that satisfies equilibrium conditions is the one that minimizes the total potential energy, where the potential energy is the sum of the strain energy and the potential energy of the external loads. By applying a mathematical technique called the calculus of variations to minimize the total potential energy, we can obtain an approximate solution to the equilibrium equations. The other weak form method is the Galerkin method of weighted residuals. In this method, the function that satisfies the differential equation is approximated as the sum of a number of assumed trial functions that each have unknown coefficients. This approximate solution is substituted into the differential equation, and an equation for the error called the residual is obtained. If we multiply each trial function by the residual and set the integral of this product to 0, we can calculate the unknown coefficients that minimize the residual. This gives us an approximate solution to the differential equation. This is a more widely applicable approach than the principle of minimum potential energy, but for stress analysis problems, both methods give the same result. Regardless of which method we use, we end up with a stiffness matrix for our element. But to apply these methods, we need to be able to describe how displacements and other field variables vary inside the element, instead of just at the nodes of the element. To overcome this issue, an element needs to have a defined function that calculates values inside the element by interpolating the values at the nodes. The shape function is just an assumption. It's usually chosen to be a polynomial, since they're relatively simple and sufficiently accurate. And with that, we've covered all of the key aspects of the finite element method. In summary, the first step in the finite element method is defining the problem, including the relevant material properties, loads, and boundary conditions. Next, the body being analyzed is split into a number of small elements connected at nodes, and the element types are chosen. Then, a stiffness matrix is defined for each element, using one of the three methods we covered earlier. The element stiffness matrices are then assembled into a global stiffness matrix based on element connectivity. This global stiffness matrix defines how the structure will respond to applied loads, and we can use it along with boundary conditions to solve for the displacement at each node in the structure. Once we have displacements, we can calculate stresses, strains, and other field variables of interest. Then all that's left to do is post-processing to obtain the desired results and validation of the model. A lot of the hard work, like calculating the element stiffness matrices, assembling the global stiffness matrix, and solving the model, is done by the software being used. But the engineer is responsible for making sure that the problem has been properly defined, that the mesh is suitable, and for interpreting and validating the results. I hope this video has helped you develop a better understanding of the fundamentals of the finite element method. If you're interested in learning more, you can check out the extended version of this video that's available now over on Nebula, where I spend a few more minutes covering the problem definition, discretization, post-processing, and validation steps. Nebula is a streaming service built by independent educational creators. It's a place where you can find extended versions of my videos, alongside amazing original content from other creators, like Mustard and Wendover, without any ads or sponsor messages. You can get access to Nebula for free when you sign up for CuriosityStream. CuriosityStream is the perfect streaming service for curious minds. It has thousands of high-quality documentaries to keep you entertained and learning, like Particle Fever, an incredible film that follows experimental and theoretical physicists during the first round of experiments at the Large Hadron Collider, the largest science experiment ever conducted, as they work to prove the existence of the Higgs boson particle. If you sign up to CuriosityStream using this link, you'll get a 26% discount on their annual plan, and you'll get access to Nebula for free, all for less than $15 a year. So to watch my bonus content on Nebula, and Particle Fever, and countless other documentaries on CuriosityStream, head over to curiositystream.com/efficientengineer, or click the link in the description. It's an amazing deal, and signing up is a great way to support this channel.